Hello everyone, my name is David and presenting with me are Evan and Kyle. We are group number 13. For our project, we have designed a vibration frequency sensor using MEMS cantilever beams. We are going to go over our design, its motivation, the designing process, our device layout, analysis, testing, and a summary conclusion. Our device measures the frequency of a given vibration. This is done through analyzing an array of cantilevers to determine which of these is hitting its resonant frequency. That cantilever will be vibrating the most and should stand out from the others for this reason. We decided to do this for our project because Kyle and his capstone team have designed a chassis for UBCO motorsports. Ideally, a vibration analysis would be done on the chassis as it experiences many sources of vibration input from engine, suspension, and wheels, and any resonance is not desired.
Our initial idea was to design a double cantilever with a centralized mass. So now to maximize the mass at the center, it would be made of both layers of SU8, and as you can see, the initial design incorporated an S-shaped spring. However, this was not ideal as it would be difficult to control the direction of vibration. Since we wanted lateral vibration, we decided that we would not go with this design. After considering the potential flaws of the first design, we wanted to simplify the design. This change would also help simplify the calculations. This led to the final design of a single cantilever with a free weighted end. This change also provided us with a cantilever that we could design to vibrate in one direction for the most part. Unlike the initial design, this beam would be composed of the second layer of SU8 instead of the first one, which I'll discuss further in a little bit. This design also allowed us to maximize the weight of the mass while minimizing the mass of the spring itself, which in this case is just the cantilever beam. For the design process of our cantilever beams, we started with fixed frequencies and a beam with a fixed height. The height, as previously mentioned, was 20 microns, as the beam would be composed of the second layer of SU8. The objective here was to minimize the size of the mass to decrease the beam to mass ratio. This decreased beam to mass ratio would help improve the accuracy of the calculations when determining the natural frequencies of the sensors. The other objective here is that we needed to minimize the sensor size so that it would not take up too much space on the wafer, as we had many frequencies that we wanted to test. So through Excel, we were able to find the optimal dimensions for the beams and masses for each frequency, which I'll further discuss in the next slide. To break down our Excel calculations in slightly more depth, we were able to determine the required equation to yield the most accurate frequency by finding the equivalent mass, which can be seen at the bottom left of the screen. For a variety of lengths and widths, the equivalent spring constants were calculated, which would then calculate the corresponding mass geometry to produce the desired natural frequency. This allowed us to calculate at least 3 different designs for each frequency. As previously mentioned, we had 3 designs for each frequency. Starting with 1000 Hz, we increased by 2000 for each frequency, all the way up to 17,000 Hz. Since we wanted lateral vibration, the design used a beam that was taller than it was wide, made of the second layer of SU8, and it was also anchored with a 50 micron anchor. So therefore, the width of this beam had to vary between 10 to 20 microns. The mass itself was composed of both layers of the SU8 to maximize the mass at the end of the beam. As you can see on screen, the larger cantilever beams and masses are associated with lower frequencies. This is because the mass is in the denominator of the frequency equation. Therefore, as the frequency of the beams is increased, the size of the sensors tends to decrease. The length of the beams also affects the equivalent spring constant. As the length is increased, the frequency goes down. We duplicated all of the sensors just in case some broke or didn't fabricate correctly. So for the first fabrication, we were actually only able to produce air, and none of our beams actually got fabricated, so therefore we decided that there was probably an issue with the actual anchors themselves. So we went back and we decided that we would increase some of the anchors from 50 microns to 70 microns, but we also hypothesized that the second layer of SU8 was struggling to bond to the substrate, so therefore we tried anchoring some with the first layer of SU8. However, the beams themselves remained relatively the same.
After design, we wanted to validate the cantilevers through a series of hand calculations and simulations. We made several of our cantilever designs on SOLIDWORKS. Cantilever you see is one of the 1000 Hz designs we have. The other CAD models we created include 5000 Hz, 11,000 Hz, and 15,000 Hz. The same simulations were run on each of these cantilevers to confirm their function and accuracy. For the deflection simulations, gravity was applied to the cantilevers. This confirms the droop would be less than the 1 micron gap between the dimples and the wafer. If they contact it, it could disturb the natural frequency. We had multiple designs for each frequency, however, only one of each was tested, and the deflections are listed. All of them are well under the 1 micron threshold. The frequency simulations were the last of the analysis on the cantilevers. The simulations showed very close results to the design natural frequencies, which is extremely promising. The difference in a few hertz would not affect the experiment. The simulations picked up on several modes of vibrations which the cantilevers will bend and distort. However, we are only concerned with mode 1 vibrations, which the displacement is completely horizontal and will prevent the cantilever from hitting the substrate or wafer surface. The other modes have much higher frequencies than what we will be testing and should not create any issues.
The cantilever's natural frequencies range from 1000 to 20,000 Hz. As this is the audible range, a small speaker, maybe from headphones, earbuds, or a phone, could be pushed up against the chip. To minimize sound damping, the speaker would ideally be pushed from the outside onto the chip side to promote horizontal vibration. Then, we can vary the sound frequency, and the cantilever with the same natural frequency as the sound being played will hit resonance and vibrate the most. If the design frequencies do not align with the testing results, the testing process can act as sensor calibration. Our initial testing plan was to simply look at the chip and see the cantilevers vibrating. Our research showed that the theoretical maximum neuron firing frequency is 1000 times per second, so optical neuron firing would limit us to noticing anything more than 1000 Hz. The small deflection would also be very difficult to notice without sufficient optical assistance, thus this option may not be viable. Our next option was to use video recording. Due to the high frequency of our cantilevers, a regular 24 to 30 frame per second camera, such as the lab microscopes, would not be able to capture the motion. There are of course other cameras capable of the necessary frame rates, but they are extremely costly at over $100,000. Potentially a cheaper video camera or even a phone could work to sense the movement by using the strobe effect at a synchronized frame rate, but this would be very difficult. Our third method, and likely the most practical method, is to use photography to capture the motion blur of the sensors. The Nyquist sampling rate suggests taking samples at roughly double the frequency you are trying to measure. Using this concept in reverse, by setting the photo exposure to about half of our sound frequency, the motion blur should peak for the cantilever at that frequency. While unable to test our sensors, we learned a lot about basic MEMS devices and how even a fairly simple cantilever can have complexities making it very difficult to fabricate. This project helped us to see the importance of including different design variations to aid failure analysis, and led us to reconsider some of our design decisions. If we were to repeat this project, we would potentially decrease the frequency range to allow for more variations in the design and use the discussed testing methods for applying vibration and observing the MEMS device.